Everyone. Today is going to be my first video on this channel, and we're going to go through the problems from EGMO 2025. I haven't looked at the problems yet, and I don't know the results yet. I know like slightly some results from the countries and people um, that are my friends, but I don't know the cutoffs. And what we're going to do today is we're going to live solve day one. I don't know how long it'll take me. Will I be able to do everything? Right after that, we're going to do day two tomorrow. And the plan is just to see where we at, just to show how I approach problems, and that might be useful to a lot of people. And genuinely, what I want to show on this channel is different problems that I'll be sharing and my solutions and my personal approach to them, because I think that that will benefit both the viewers, as it might show some different approaches and some um, small minor details on how I approach the problems that might be useful to beginners, maybe. Or as well, I could maybe look back at how I think and look at your feedback and also improve my skills, because I'm still learning. And yeah, I think that'll be a very good experience for me. So I hope you will enjoy this content. And if you do, please let me know and share and subscribe to this channel. And we're gonna start. So we see that we have number theory, some algebra, and Geo. And personally, for me, Geo is my strongest. So when I see Geo at the third position, I'm very eager to see what it's like. So let's just go and have a look at it. I know GeoGebra isn't allowed in contests, but um, for the sake of just quick and good diagrams, we're going to use it today. As a general advice on how to get good at geometry, I think that GeoGebra is a very good tool because it helps you to remember constructions much better. And a lot of geometry is just intuition. So it's just a sort of just seeing patterns that are the same in different questions, and then like different configurations that are the same, and just a lot of it's about intuition. So yeah, I mean, and let's just start. So let be ABC be an acute triangle and points BDE and C line and a line in this order and satisfy BD equals D equals EC. So you have an acute triangles ABC and then DE such that BDEC line in this order that BD equals D equals EC. Um, that's already a tough construction, to be fair. I mean, splitting the triangle into three parts is not that easy, but the beginner method probably is just something like adding a point, midpoint here. I'll just name it I so that I can cancel out this point. Um, yeah, or even faster. It's like adding 0 points, and then what we're gonna do is we're gonna take this triangle like this. We're gonna mark the centroid I. And that what we're gonna do. Well, it's not the name. I just don't need it that much. Yeah, I just want to. We just see that column I is not involved. And for me personally, I don't like to name like random points with I or H, because like worth a sentence or whatever. So we have a condition ABC is a triangle such that BD equals D equals EC, and then M and N are the midpoints of AD and AE. So we have M here, um, and we have M here. Okay. And now we say that ADE is a Q, and we look H as its orthocenter. So we have an orthocenter H here. Well, how should I do? Something like this, I guess. Okay. ABC won't be quite like a Q, but I don't think it'll matter unless we have the orthocenter of ABC. Okay, so H is the orthocenter of triangle AEE, and T and Q lie on lines BM and Cn such that DHMP and EHMQ. So you have lines PM and Cn, and then we have circles EHMP and NHEQ. So this is point P, this is point Q. Okay, and we need to prove that PQ and M is concyclic. Okay, this doesn't look that bad for EGMO. I wouldn't say EGMO is a particularly good Olympiad for Geo. Like the past years, especially, the Geo wasn't that bad, I'd say. Like it was quite simple. So here's our problem. And that's the first thing that we will note is that like my at least my general approach to geometry is we want to get rid of points or add points that um, just work together. So there's a concept of bad and good points in geometry, and bad points are like points that we don't quite understand, and good points are like the points that we understand that we know a lot of facts about. So A, D, E, we know a lot. B, C are like meh, but we still know them. They're quite well defined, but and same with points M and N and H. But on the other hand, the only points that we don't like is P and Q. So, and there's two ways to approach bad points. The first way is to delete them. So rephrase the condition on these points such that we don't use them and work only with the good points. And the other one is to add some other points that are also nice, and that will help us to understand the P and Q points. So in this problem, I think that the main thing that we see is like these lines that are quite these lines like CN and BM, I mean, there's no Humpty points on these lines, Q and P are probably not Humpty points. Um, and that's why it just feels like everything is based on medians and equal lengths. So for me, I think what I would do is I would reflect B over M and C over N just to like continue these medians. And I think as well what helps is that BH, that these are collinear. I mean, not with H, but B like this. Um, yeah, like this. This works. And we're trying to show P, Q, and N is cyclic. Well, and clearly a B prime C prime is parallel to BC. So the only thing that we want to show is that C prime, P, Q, and B prime, they're concyclic. Um, just because Mn is parallel to D and is parallel therefore to B prime C prime, and PQ is the anti-parallel. So that's a term that is used. So basically, Mn is parallel to C prime B prime, and if PQMN is concyclic and works the other way around, this angle is equal to this angle is equal to this angle. Oops, this angle because of parallel, and this equal to this. Um, So now what we want to show is that PQB prime C, it's the same as showing B prime C prime is cyclic, but we can see that H may also land this circle. So I think that's the way to go. So, and turns out it does land the circle as we see. So now what we can do is we can get rid of point Q because and point C as well. The reason is everything is based around triangle ADE anyways. And now we can get rid of all these points and I'll show why. So we can get rid of this, get rid of this, um, get rid of point B as well. Um, so yeah, we get rid of the points that we don't want. So B and C were always kind of like hanging in there. So now what we want to show is we have a triangle ADE and triangle ADE. E is reflected, the midpoint gets when C prime, B prime is reflect is the same as like C prime, but the other way around. D prime M intersects a circle DH and P, DHM at P, and we want to show that this is concyclic. I think there's two approaches or an axis for angle chasing. Um, so something like red axis would involve adding this point, but the problem is that like this circle and this circle, they don't really work together. Um, but I think angle chase, so which angles can we look at? I think the only angle from this circle that is common, like it's this one. And it's equal to this angle, which is nice. Okay. So this angle is so this if this is A, say alpha, this is 90 minus alpha, and this is 90 minus alpha. And yeah, I think the last piece is that when we have a triangle ABC, and it's a very, I think I see the end. So the idea is when we have two parallelograms like this, if we build a third one, then the orthocenter is the circumcenter of the big triangle because this is equal to this. So this is a perpendicular bisector of the side. So it's the circumcenter. Um, yeah, and for this reason, we get that if we reflect a above the midpoint of DE, so we intersect basically these two lines. So let's just go ahead and something like this and call this point F, right? Then H is the circumcenter of this. Then if this is alpha, this is 90 minus alpha, this 90 minus alpha, this is alpha as well, and then this is 90 minus alpha. So the thing is cyclic, so we're done. Um, I think this is quite easy for a P3 on EGMO. Um, I think we're done. Yeah, because Q lies and that's on D prime H, C prime N. P does, and we're done. I mean, I'll be honest, I expected a bit more. Um, I don't really like this question. Uh, I don't like it. I just feel like I just feel like these conditions, they were all very, very simple. I mean, and there was no config part in it. There was like I don't like I know that a lot of some people don't like config geo, some people do like it. But I think that some elements of config geo of like a lot of points uh interacting with each other, like not two or three points, but like a lot. It's a very good concept that you want to see in P3s. So I mean the sad part is probably this problem would be like P1 on IMO or something. I mean, I can't see it being P2 even. Maybe like a hard P1 or a very, very easy P2. Like very easy P2. But I wouldn't put it at P2. Maybe it's like a G2 level problem, maybe even lower. I mean, I think there are G2s that are way easier than, that are way harder than this. Like, okay. Okay, now we can go back to our normal order and look at problem one. Um, so for a positive integer n, let C1, so on, C2, Cn be all positive integers smaller than n and coprime to n. Okay, yeah. And find all n more than or equal to 3 such that the GCD of n and Ci plus Ci plus 1 is not equal to 1. Okay, so basically we have like a number, say 6, that's more than 3, whatever. And we write all the numbers that are coprime. Yeah. So it's like 1, 5. Well, this is quite short. And then we look at the sum and we say if it's not equal to 1, then we're fine. So this one works. But say like if we take 11 and prime and whatever, just 1, 2, 3, 4, 5, blah, 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 blah. And 2 and 3, they add up to 5. That doesn't work. So, okay. in these problems, like I don't think a lot of people can see the structure immediately. So every question has a sort of a structure that you want to explore. And I think that looking at small case is one of the best things you can do. I mean, everyone does it, so I don't think I need to go on and rant about how useful this is. But I think it just, if you see a problem, and this is the thing I actually got inspired from by Evan Chen. So I looked at his streams as well, and I think that whenever he saw a problem, it didn't matter if it's A1 or N1 or C1 or whatever. He always looked at small cases, and I felt that that's quite cool because I thought that personally that like the guy is very, very good at why would he have to look at small cases? And I think if you don't let ego to say, oh, this is easy, I need to solve it in like 2 seconds, then you might go like then you need to ignore that feeling and yeah. Uh, okay, just go to six, we check that it works. Um, so yeah, I think that after that, like first thing I always do is look at small cases before even looking at structure and trying to find anything. Here it's two and three doesn't work. Primes don't work for sure, except for three. N equals eight, one, three. Okay, so we know that even ones work. So the reason why even work is because all numbers co-prime to an even number are odd. And so it's a string of odd numbers, and the sum of any two adjacent ones is even as well. And if it's even as well, then even and even, they both divide two, so they're both divisible by two. Um, and so the GCD is not one, so they both work. Okay, for odd now, we know that n equals 3 works. We know that 7 and 5 don't work. Primes don't work. N equals 9. We have 1, 2, 4, 5, 7, 8, 3, 6, 9, 12. Okay, so I think that if it's divisible by 3, then it works. Let's see what's the reason. Um, hmm, let's check a bit more. So n equals n divisible by 3 and odd, maybe that works. So 15. So now we just look at odd numbers, just to make it clear. 1, 2, 4, 5, we skip 6. No, 6 we skip 7, 4 and 7, 11. Okay, so 15 doesn't work. So it's probably powers of 3 then. Um, Powers of 3 do work because for powers of 3, the only numbers we clear out are the ones that are divisible by 3. So the way I think about it right now is that we have like a string of all numbers, and then we just cross out all the numbers that are not coprime. And the only ones that we cross out when n is a power of 3 is the one that are multiples of 3. And so we get numbers that are 1 and 2 mod 3, and they're in the order like 1, 2, 1, 2, 1, 2, and 2. So the sum of two adjacent ones is always divisible by 3, so it works. So we know that n equals 3 to the power of k works. And I assume that now the other ones don't work. So we check 15. I think that's good in our case. Let's just think about why does it not work. So, hmm, so let's look at an odd number, 2n plus 1. And then we have 2n and 2n minus 1 are co-prime to this number. So their sum is 4n minus 1 is not co-prime to 2n plus 1. So we go like in contradiction. So 4n minus 1 and 4n plus 2. So they both must be divisible by 3. So I think here's where the 3 emerges from. Yeah. So okay, so the only one reason is when it's divisible by 3. So we can't get away just by doing that. So if we want to get rid of threes, I think that we can get the threes out. So 3 to the power of alpha times some m. And then we look at so again, if we look just on this won't work. If we look on like we need two ones that are co-prime. So I mean the problem will be with factors of n. So if we look so basically the problem probably what we have is that we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then we cross out all the ones divisible by 3, and we basically get these pairs. And I think maybe the problem that emerges is that the first time when we cancel one out, this sum might be divisible by some factor of n. But we're going to try to show that that's impossible, maybe. So say 7 or whatever, some number is the first one that is crossed out. So it's going to be a prime, the smallest prime that divides n, to be precise. So say P is the smallest prime that divides n, then it's being crossed out in its pair. Now, then we get this one, and this is not divisible by 3. And this could be either P plus 1 and P minus 2, or it could be P minus 1, and then we cross out a number, and then it's P plus 2. The sum of them is 2P minus 1 and 2P plus 1, and 2P plus 1. Okay, they're not divisible by 2. That's the bad part. So wait. Yeah, we don't get a contradiction because if 2P plus 1 is a prime, then we get a contradiction. Okay, so probably prime factor is not the way to look. Maybe we should just take n. I think that's the second thing that comes to mind. If we just get rid of n and we look at numbers n minus. So it depends if n is 1 what 3, then we'll n plus 1. And n plus or minus 1 second. So if we look at like string n minus 2 and minus 1 and so on and plus 2, if these are numbers we have in a row. If n is 1 mod 3, then this one is crossed out and this one is crossed out. Um, and then we have that n is getting thrown out. So this one is being left. I think this one is being left n minus 2 because n minus 2 is not it's not even. So n minus 2 and n are co-prime, and n minus 2 is not divisible by 3. So therefore, 2n minus 1 is the sum of these two numbers that are going in a row. And 2n minus 1 and 3 alpha to the n are co-prime because this is 1 mod 3, so we get rid of this, and we're done in this case. I assume n equals two cases similar. So if n is 2 mod 3, then we get, what do we get? We get that n minus 1 works. And so and we have a string n minus 1 and n plus 1 and n plus 2. So n plus 1 is divisible by 3. N is divisible by n minus 1 works, and n plus 2 works because n plus. So here's where we use the even part. So n plus 2 is divisible by is n plus 2 and n are co-prime, and therefore the sum of these is 2n plus 1, which is co-prime to 3 to the power of alpha n, because this is 1 mod, no, this is 2 mod n, and it's not divisible by n, so we're done. So, okay, I think this is not that bad. I think problem 1 is even harder than problem 3. Or, like, I think that maybe not harder. I mean, like, they're comparable, though. I mean, I can't say that P3 was hard at all. Like, I just can't say that P3 was hard. And I know that I'm good at Geo and that my opinion may be biased, but I just don't see how P3 is a P3 because I just feel like it was way too simple. It just was way too simple. But yeah, and we have just P2 now. We have the P2 now. So yeah, let's see what P2 about. So we have an infinite increasing sequence A1, A2, A3. Positive integers is called central for every positive integer, and the arithmetic mean of the first n terms is equal to a n. Ooh, this looks pretty interesting already. It gives me the vibes of that A4 2013 or something. I don't remember. I don't remember. I'll be honest. It was something like inequalities A1, A1 like less than n squared, and you had to show something like that. I don't remember. Yeah. So show that there exists an infinite sequence B1, B2, B3 of positive integers, such that for every central sequence, there are infinitely many positive integers. And oh, this looks interesting. Okay, so the first thing that we see about this problem is the structure of the central sequences must be like quite rigid, and the reason is because we have like some fixed, um, we have a fixed sequence Bn, and the sequence it has infinitely many terms that are the same, and that is very odd. That is very odd. Um, and the reason is odd because you don't get like normal two sequences to have um, any sort of terms that are equal for sure. And this means that as well, we get that the sequence can't go like the sequence of any central sequence. It can be like very big or very small compared to some other one. Um, so it's kind of like very limited and very rigid in its structure. So, and in order to approach this, I think what we have to do in this question is just look at the structure, try to. So, I think first thing that we need to do is guess what kind of EN do we need to like just generally look at the structure and try to find different stuff. Um, from the first point of view, just not looking at the problem, I think that maybe what will work is just saying that like we get strings of 1, 2, 2, 2, 2, 3, 3, 3, blah, and we just get big chunks. If we just get big chunks of numbers, maybe that will work because what the whole problem is about is that the sequence can't go astronomically big or astronomically smaller than some other fixed one. And so the position of certain numbers might be fixed in terms of like where they can be along the line. So maybe that's the thing that we need to explore. So yeah, let's go ahead and do that. So we know that just let's write the problem statement first. So the sequences that we're looking at is where arithmetic mean these numbers is this. Okay. Okay, this is a quite big A at the noise. Um, Yeah, I think that's the way we go about it. Though I don't really want to have the divide by A thingy. And I think the most logical step we can do now is look at the next one and just say that it's n plus 1 squared and subtract these two. Now, what do we get? We get a n plus 1 plus so on plus an plus 1 is equal to n plus 1 squared minus an squared. Okay. Um, so the other funny thing about this is that here there are an plus 1 minus an numbers. So the arithmetic mean of these numbers is the sum of and n plus 1. That's pretty cool. And I think the way we can depict it, right, for us, for at least for myself, my brain doesn't work um, algebraic, phew, algebraically the best. For me, my brain works the best when I have a picture in front of me and when I can look at it and say, okay, I see what's going on. This is the type of problems I feel the most comfortable at solving. And when I can't describe what's happening visually, or at least with some formula, then but even in case of some formula, for me, it might be very hard. So if you can relate to that, I think that, and for all people in general, like, I think that drawing some diagram that represents what's going on is always useful. And the way we can depict what's going on here is we look at A1, so we look at A1, look at A2. So because the only things that we are actually given information about is only numbers that are of this type, and we're not giving about anything else. We just know that the sequence is increasing. And we know that between these two numbers, so if we say numbers, and here we go arithmetic mean, then here we have an plus 1 minus n, wait, we have a2 minus a1 numbers with arithmetic mean of a2 plus a1. That's the average value of number in between them, and we look at them like this. So, and then here we have A3 minus A2 numbers with arithmetic mean of this. And finally, we have A4 minus A3 with arithmetic mean of A4 plus A3. And this list goes on. So an obvious bound now that we can get is bound like this number in between the average mean here and average mean here. And just generalize it and we get that AI is more than AI plus AI minus 1 and less than AI plus 1 plus AI. Yeah, so I think that's really quite good because this kind of says that the sequence can't go very, very large because if the sequence does, then the problem is that, well, the difference between the index of AI and I, if it's very large, then this just won't be true. So the sequence is quite limited to where it can go. So, and that's quite useful for us. But it's bounded from both sides. So it can't be both very small and both very good. So that kind of supports our theory about like, well, it's not theory, it's a fact that the sequence is like quite rigid and quite almost fixed in its structure. But it was a fact that we just found more evidence to it. Um, So I think we like for A1, I'm not sure what's happening for A1. Let's just go ahead and maybe try to find some. So yeah, we forgot to look at small cases and small examples. So let's just go ahead and try to find different sequences and central sequences and just try to bound them. So we have like first number, say 2, right? Then the second number, the meaning of this might be okay. Okay, I think that okay, the first number must be 1. We didn't notice, but A1 must be 1. If A1 is something more than 1, then the mean of the first numbers, A1 numbers, is the smallest number on the list. So that's impossible. Yeah, that's impossible, and so A1 is 1. Therefore, we have that. Okay, we get this. Now, now let's just go. I think there's not one central sequence, but let's just plug in and say, okay, we can't plug in 2, we can't plug in 3. So 1, 3, then the next number, the first three numbers, their GCD is 3, so this one must be 5. And then we have first 5 numbers, their GCD is 5. So we can like pair up it nicely. It's like 7, 9. Okay, so I think the sequence of odd numbers, it works. So just the odd numbers sequences works because for any odd numbers, we just have it's the arithmetic mean of these ones. So odd sequences work, and I think maybe then my theory that it's just a spam of numbers doesn't work, and it's just Bn just might be the sequence. So yeah, it might be the sequence because it's and the reason is it's quite nice. It's Um, at least we have one term always that's the same. It's 1. So let's see what happens when it's like the first term is not 1. Say 4. Okay, 1, 4. The GCD of first 4 numbers is 4. The sum of them is 16. So the sum of these two is 11. It must be 5 and 6. Okay, then the first 5 numbers, the GCD is 5. So 25 is the sum. We already have 16, so this is 9. And we get the 9 here. So that's pretty cool. And then what's the next one? Some of these is 25. The next one needs to be some of 6 numbers is 36. So this is 11. So yeah, I think this is quite nice. And I think this proves that Bn is probably the sequence we're looking at. Um, so this now, I think now this part doesn't play that crucial role. I mean, it plays a crucial role maybe to bound the sequence, but my theory that it's just bounding and then saying that like we spam 1s, we spam 3s, we spam 5s, or whatever doesn't work. It just doesn't work. Okay. Okay. Let's see. Um, well, the thing is, another thing that we know is like if we have a AI, right? Here we have a AI plus 1, and here we have a AI minus 1. Here we have AI minus AI minus 1 numbers. Here we have A plus 1 minus AI numbers. And here we have so this is numbers, this is arithmetic mean. So the arithmetic mean here is AI plus A minus 1. Here it's AI plus 1 plus AI. That's great. Um, so now what we're trying to like what the problem is that the amount of numbers that we have here is quite small. and the difference here is quite. So thing is like here in total between AI and AI plus one, we have AI minus one numbers, and the like the difference between these two arithmetic means is also AI minus no wait, it's AI plus one minus AI here minus one, and the difference between the arithmetic means it's the same. And so if we just knew that, since we know that everything increases at least by one, then it's kind of like uh, it means that the structure is quite neat. But if it was at least two, then I think we're fine because if all the differences were at least two, then we know that the hops of between like these two numbers, the differences between one gap and the other gap is 2AI plus 1 minus 2AI minus 1. But the differences in GCD is like AI plus 1 minus AI. And I think that's the only time it actually works is when all the numbers are plus 2 plus 2 plus 2, like we had in the plot sequence. So I believe, so wait, um, yeah, if the difference between everyone is at least two, then the GCD couldn't have been the difference between the arith why am I saying GCDs? The differences between arithmetic means on the interval between AI minus one and AI and AI plus one, like in this interval and this interval, the difference couldn't have been AI plus one minus AI if the differences are at least one difference is strictly more than two, and all other ones are strictly more, are at least two. So the only case that works is when it's all two or there are ones. And ones are quite nice. So as we saw in this thing, like if we look further, when we look at nine, we can't have any information here. But when you had six or five, we can restore our number in a single way. And the other thing I think that the way, like probably more logically would be to come up with this is when if I just looked on why these numbers were the same. So say what happens if AI n plus one, AI n equals to n minus one, and just maybe look backwards on what happens. But let's just say B, C. So let's suppose an equals x and n plus one equals x plus one. So that means that a1 plus so on plus ax is equal to x squared, and then a1 plus so on plus ax plus 1 equals x plus 1 squared, which yields x plus 1 equals 2x plus 1. That's pretty nice. I think that's what we want. So this sequence Bn is just 2n minus 1. So we get that this term is the same as in the sequence. So if we say that some central sequence doesn't have infinitely many terms of Bn from certain moments, there are no terms that differ by 1. This means that all terms differ by 2. That's the only case where this holds because, well, it's just calculations. But it's to me, it's pretty clear that when when you try to space out, go from the smallest to 2, because the means are a minus 1, and a plus 1 minus ai, um, the difference between arithmetic means if there are this amount of numbers here, like if there are in total this amount of numbers, and their total GCD is a plus 1 minus ai. Um, so the difference between these amount of numbers is a plus 1 minus ai, and the same is the difference between a plus 1 between the amount of numbers, then like the GCD might be um like 1 or whatever. Um, Oh, 1 second. Uh, let's see. 1 second. Let's just do it rigidly. So we have the GCD. Um, if we have the arithmetic mean of these ones is this, and differences are at least two. Then we hop from this one by two into a minus a plus one hops, and then we go the same way the other way. We know that the difference between, if we have like a line, so if we have like numbers here, and this is the arithmetic mean, we have a number here, and this is its arithmetic mean, then basically we know that there are there are like, if this is less than this on x, then there's x more numbers here. And this means that if we go by jumps by two, and we go here, but we have like two times less, we have n less jumps, and the GCD will be then the same only when, so to illustrate the point, if we had a number 11 and we go to 13, 15, 17, and we look at the GCD of these, it's 15, right? And then if we look at, say, 9, 7, the GCD is 9, and we had what? Um, 1 second. Oh, I thought I got it intuitively. I think I get it, but let me just see if we can get it strictly. So we have AI, and we know that the GCD between this number and this number is AI plus AI minus 1, and there are this amount of numbers here. And then we have this one and this one. So the amount of like steps we can get to here, and plus the same amount of steps there, that's like the farthest away number we can get, I assume. So, okay, we need all the differences, or at least two. Hmm. Intuitively, I get it. I don't get it strictly though, and that doesn't make me feel comfortable. Mm, okay, we had some numbers here, and then we jump by at least two every time. So here, two, 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 oops, two, 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 and we're trying to minimize the difference between them. So to minimize the difference between them, we want this one to be as close, so it's like two, always here, and this one to be as close as well. So we're trying to bring the like geometric place of point, center of points here as left as we can, and get from here as right as we can. And we do that by doing the smallest shifts ever, which is two. So that's the best approach. And when it's just two, they're all shifted by two. Um, if we have k numbers here and n numbers here, then we have the center of masses. Well, here it's n times n minus one divided. So that's the sum of all points and their endpoints equals 2, 4, 2n. Yeah. And then here it's similar way. It's like negative though, but you get it's like we cancel here, we get n minus 1, here we get k minus 1. The difference between the ones is n minus k, which is difference. Okay, yeah. So that's the minimal one. N minus k, it's strictly achieved when all the jumps are two. That's what I was trying to do. So the n minus k difference, so this difference between the amount of numbers and the difference of AMs, it is achieved only when it is achieved. We showed it's achieved when the differences are two, and it is exactly achieved. And we showed also it's the best case. So it's a dodgy technique to say it's the best case. But here, in order to get the points as closest as possible, we want to just get closest to here. And we just showed it's like when the jumps are all two. So, and if it fails, if it's not two, then of course we're busted. And it means that all differences are two from certain means. And if they are, then let's see what happens. I mean, if all the jumps are two, then from certain moments we have AAI. So we just look at the sequence from certain moment. This is a bit okay. I don't want to do it. I want to say that it's ended already, but we can't do that. Okay. I see how to do it. So if we have two numbers that differ by two in a row, then what we can say is that if they're odd, I assume we're done. Oh, why do they have to do it so complicated? Okay. Um, so we have like certain numbers, one and certain numbers, and then we have all divided by two. So first case is when they're all even. So we have 2k plus 2, 2k plus 4, blah 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 blah. Um, in this case, okay, let's see it. Can we work backwards? Can we work backwards? Okay, the other thing that we note is that the GCD, oh, GCD, I'm so sorry. I don't know how many times I say GCD and then correct myself. But AM, the AM of these numbers, it must be so mm, n points away from the center. Oh, Okay, so if we always get this, then the AM, so the AM of the number A2K. So let's say, okay, let's just, I tried to find something nice. I don't think that works. So let's say AI is K, and then AI plus T equals K plus 2T. Okay, then we know that A AI it should be what? Oh, this is killing me. Okay, say we have 10, 12, 14, 16 for a certain moment. Then we know that this is so complicated. Ah, all the differences are two. What did I do? What do I do? Okay, so mm, all the differences are two. What are we going to do? Yeah, I think I see it. Okay. Um, maybe I see it. So we look at these two. So this is AK, and this is AK plus 2. Um, and this is equal to the sum of A1 plus so on plus uh, wait uh, uh, A1 plus so on plus AI plus A1 plus so on plus AI plus AI plus 1. So sorry, if we just delete this. If we say A1 plus so on plus AI equals to, say, AAI, right? AAI. It is equal to AI squared, just K squared. And we have A1 plus so on plus AI plus 1. Yeah, I think we're done. But one second, I'll just finish this up. This is equal to AI squared then, or K squared. And then we add, so, well, on one hand, this is equal to K plus 2 squared. So it's equal to AI plus 1 plus 2 squared. On the other hand, it's K plus K squared, which is sum up to AI. And then we have AI plus 1 and AI. So AI, and then, so we have like this equal to A1 plus so on. So AK plus AK plus 1 plus AK plus 2. So sum of these is K squared. Um, yeah. And This is k plus 2. So this number must be k plus 2 as well. And I think that's contradiction. Wait. Or is it k? One second. Wait, why does then 1, 3, and so on work? Uh, oh, wait. Yeah. Of course, I made a silly mistake. AK plus 2 is k plus 4, or k plus what? AK plus 2. Oh, Jesus. This has to be so complicated. One second. Yeah, this is k plus 2 and this is k plus 4. So, wait, so what's... We know that we have certain numbers. Then some from here are all difference too. And then we have a number that's like AAI. So it's like AK. Next number is AK plus 1. Next number is AK plus 2. And the AK plus 2 number is AI plus 1. So because A plus 1 equals K plus 2, this is AI. So A of AI. So the sum of these numbers is K squared. And the sum of these numbers is K squared plus 4K plus 4. Okay. And then, so the sum of these two is 4K plus 4. And since they must, since like, since this number, since all the numbers must differ by 2, this number must be K plus 3, and this is K plus 1. Okay, here we go. So, no, not K, 2K plus 3, and this is 2K plus 1. Because two adjacent ones from this moment all are divisible by 2, we just hop into a K. These two ones have to be the difference too. So this 2K plus 3 and this 2K plus 1. So the difference of two ones sequence is the same as the sequence we had in BI. So we're done. Okay. Um, I think in general, problem 2 wasn't that bad. I quite liked it as well. Problem 1, not that bad, but also not that good. I didn't like it that much. Problem 3, I just thought it's bad. But anyways, I'm very thankful for anyone who watched this video, and I just want to wish you a good day, and thank you for watching and solving the problems with me. Um, let's just see how the content, like at last, let's just see how the contestants do on day 1. Um, so scoreboard. So wait, is there? Okay, yeah. So China 42, 38. So question 3, I assume somebody solved question. I think question 3 is hard. Question 6 is hard. Okay, question 6 is very hard. I think only 2 people solved it during the contest. Um, so and some okay, so that's pretty impressive. Um, P3, yeah, you can see that a lot of people solved P3, like a lot of people. Wait, that's P4. Wait, what? Okay, not that much people solved P3. P2, yeah, I mean, maybe it's some pressures, but I thought that P3 wasn't that bad. But anyways, I want to thank you for watching this video and have a good day. Thank you, everyone.